Good morning, friends. I am Divya Malik, student of BSc Chemistry Honors First Sem. Today, I will discuss the Inorganic Chemistry chapter Covalent Bond. A covalent bond is formed by mutual sharing of electrons between the combining atoms of the same or different elements. The atoms involved in the formation of a covalent bond constitute equal number of electrons for sharing in order to acquire configuration of nearest noble gas. The pair of electrons which constitute the bond between atoms is called bond pair of electrons. If there is one bonding pair of electrons between the two atoms, the bond formed as single covalent bond. On the other hand, two or three pairs of electrons between two atoms constitute a double or triple bond respectively. According to Lewis' concept, the covalency of an element is the number of electrons which its atoms contribute for sharing while forming a covalent bond. For example, the covalencies of hydrogen, oxygen and nitrogen are 1, 2, 3 respectively, as H bond pair H और covalency होगी इनकी 1, O double bond O covalency is equal to 2, N triple bond N covalency is equal to 3. Theoretical treatment of covalent bond. The simple picture of covalent bond does not tell us anything about many interesting questions such as arrangement of electrons in molecules, the shape of molecular orbitals, energy levels in molecules, etc. Like atoms, we can write the Schrödinger wave equations for describing the behavior of electrons in molecules. However, it is very difficult to solve the Schrödinger wave equations for the molecules. The solutions can only be obtained by using certain approximations. There are two approaches which are commonly used. These are: first, valence bond theory; second, molecular orbital theory. Both these methods are based on the variation principle or method. Variation principle. It is a mathematical technique to calculate the lowest energy state or also as ground state of the system. The basic idea of the variation principle is that V naught is the wave function for the ground state, then the energy corresponding to this wave equation E0 या E naught is always less than that associated with any other wave function that might be proposed. In other words, no proposed or trial wave function can wave energy less than the true energy of the system. This method is illustrated below. The energy of a system can be calculated from the equation. This relation can be used to calculate the energy of the system by knowing the value of this wave function. Now suppose we guess a particular wave function which may not be the correct wave function, then the corresponding energy can be calculated by using the above equation. Now let us guess some other wave function which gives energy E2. Then according to variation principle, the calculated energies E1 or E2 are always generally than the true ground state energy E naught. Moreover, the wave function which gives the lower energy state or closer to ground state is mean approximation. For example, E1 is greater than E2, then E1 is better approximation to energy and V2 is better approximation to the wave function. Valence bond theory. The valence bond theory was put forward by V. Hitler and F. London in 1927. It was improved and extended by Lee Pauling and J. C. Slater in 1931. The basic assumptions of this theory are: first, atoms do not lose their identity even after the formation of the molecule. Second, the bond is formed due to interaction of only the valence electrons. As the two atoms come closer to each other, the inner electrons does not participate in the bond formation. Third, during the formation of bond, only the valence electrons from each bounded atoms are their identity. The other electrons remain unaffected. Fourth, the stability of the bond is accounted by the fact that the formation of bond accompanied by release of energy. The molecule has minimum energy at a central distance between the atoms known as internuclear distance. Larger the decrease energy, stronger will be the bond formed. Valence bond theory, formation of a hydrogen molecule. Consider two hydrogen atoms Ha and Hb. When the two atoms are far apart from each other so that there is no interaction between them, the wave function of the system may be written as wave function is equal to wave function of A into wave function of B, where wave function of A is the wave function of Ha atom and wave function of B is the wave function of Hb atom, which we bring the two atoms closer together to form a covalent bond between them. There will be interaction between them. The variation interaction rate is the interaction between nucleus of one and electron of second, and repulsions between the nuclei and the electrons. The system may be represented as Ha1 2Hb, where 1 represents the electron associated with Ha and 2 represents the electron associated with Hb. The combined wave function may be written as wave function is equal to wave function of A1 into wave function of B in 2, where wave function of 1 and wave function B of 2 are the wave function for the separated atoms A and B respectively. Figure 1. The interactions between two hydrogen atoms when they come closer together. Using this wave function we can calculate the energy of H2 molecule as a function of internuclear distance r. These energy changes are shown by curve 1 in figure 2. It may be noted that the energy of the two isolated hydrogen atoms is conventionally taken as zero. It is clear from curve 1 that when the two atoms approach each other, the energy of the system starts decreasing till a certain minimum value is reached. This stage corresponds to the formation of H2 molecule. The fall of potential energy is called bond energy. The bond energy given by the fall of potential energy as shown in the graph comes out to be only 24 kJ per mole. The experimental bond energy for the formation of H2 molecule has been found to 458 kJ per mole. This has been shown in figure 2 by dotted lines. Comparison of bond energy given by curve 1 and experimental bond energy shows very poor agreement. Moreover, the minimum is found at an interaction distance of about 0.90 angstrom, whereas the experimental bond distance in hydrogen molecule is 0.74 angstrom. Evidently, the wave function as calculated from equation 3 is not correct. This means that some interactions between the two hydrogen atoms have been ignored. The wave function was further improved to get the bond energy value comparable with the experimental value. Improvements. Some of the improvements are discussed as below: exchange of electrons, screening effect of electrons, ionic character of HH bond. Resonance and resonance energy. The valence bond theory results into concept of resonance. According to valence bond theory, a molecule of hydrogen cannot be represented by a single structure, which could account for the stability of the molecule. In fact, a molecule of hydrogen may be described by the following structures, which have ionic as well as covalent character. It has been discussed earlier. The actual wave function and the stability of the molecule is obtained by suitable combination of the wave functions of these three structures. In other words, the actual structure of the molecule is not represented by any one of the structures but can be represented by combination of these. The contribution of each structure can be determined by its nature and stability. The actual structure of the molecule is considered as resonance hybrid of these structures. The phenomena is called resonance and the individual structures are called resonating structures or canonical structures. These resonating structures are drawn with double-headed arrow between them. It may be noted that none of the resonating structures have real existence. Also, it does not mean that the actual molecule exists for a certain fraction of time in one form and for another fraction of time in another form. In fact, the actual structure has no pictorial representation. The resonating structure are only in a convenient way of picturing molecule to account for all the properties of a molecule. The resonance hybrid may be compared with a mule. For example, like resonance hybrid, a mule has the characteristics of the donkey and the horse, but at no time it is either of these. Thus, resonance may be summarized as follows. Resonance energy: as mentioned above, the resonance hybrid is more stable than any one of the contributing structures. The extra stability of the resonance hybrid is compared to the most stable of the various resonating structures is called resonance energy. Resonance energy is thus defined as the difference between the actual bond energy of the molecule and that of the most stable of the resonating structures. Resonance energy is equal to actual bond energy minus energy of most stable of resonating structures. Valence shell electron pair repulsion theory, Vesper theory. Valence shell electron pair repulsion theory is the simplest theory for predicting the geometries of molecules. It is based on the repulsive interactions between the electrons pair in the valence shell. This theory was proposed by Sidgwick and Powell in 1940 and was finally developed by Gillespie and Newholm 1957. According to this theory, the shapes of molecules can be determined by the number of electron pairs in the valence shell of the central atoms. These electron pairs experience electrostatic repulsions from one another and the bonded atoms in a molecule adopt the particular arrangement in space around the central atom which keeps them on the average as apart as possible. Postulates of Vesper theory. The main postulates of Vesper theory are the geometry of a molecule depends upon the number of valence shell electron pairs around the central atom. In the formation of a bond, the central atom shares its valence electrons with the surrounding atom. However, in certain cases, all the valence shell electrons may not take part in the bonded formation. The electrons left in the valence shell without forming bonds exist in lone pairs. For example, in methane CH4 carbon uses all the 4 valence electrons in forming 4 bond pairs. On the other hand, in water H2O, the central oxygen atom has 1s2, 2s2, 2p4, 6 valence electrons. The hydrogen bond the hydrogen atom shares 2 of these 6 valence electrons in bond formation, leaving 4 electrons. Thus, in methane there are 4 bond pairs around carbon, while oxygen in water has 2 bond pairs and 2 lone pairs around it. According to Vesper theory, it is the total number of electron pair that determines the geometry of molecules. Electron pair tends to repel one another because their electron clouds are negatively charged. As a result, the electron pairs try to stay as far apart as possible to acquire a state of minimum energy or maximum stability. Repulsion between the lone pair and lone pair of electrons is different than that between the bond pair or one lone pair and one bond pair. The repulsion interaction decrease in the order. Regular and irregular geometries. The molecules in which the central atom is surrounded only by similar bonded electron pairs will have regular geometries, while those in which the central atom is surrounded by bond pairs as well as lone pairs will have irregular geometries. Molecular orbital theory. Molecular orbital theory was developed by Hunt and Mulliken in 1932. The basic idea of this MO theory is that atomic orbitals of individual atoms combine to form molecular orbitals. The central atom in molecules are present in those molecular orbitals which are associated with several mole. These molecular orbitals are filled in the same way as the atomic orbital in atoms are filled. Molecular orbital theory is based upon the following assumptions. First, a molecule is considered to be quite different from the constituent atoms. All the electrons belonging to the atoms constituting the molecule are considered to moving along the entire molecule under the influence of all the nuclei. Just like an atom molecule has orbital of different energy level, these orbitals are called molecular orbitals. Linear combination of atomic orbitals LCAO. According to molecular orbital theory, the molecular orbitals are formed by the linear combination of atomic orbitals of the atoms which form the molecule. The linear combination means the simple addition or subtraction of the wave functions of the atomic orbitals. For example, consider a hydrogen molecule consisting of two atoms labeled as Ha and Hb. Let the wave function for the electrons in the atomic orbitals in two atoms be A and B respectively. When these atomic electrons are brought closer, they combine to form molecular orbitals. Difference between bonding and anti-bonding molecular orbitals. Bonding MO and anti-bonding MO. First point. Bonding molecular orbital is formed by addition of overlap of atomic orbitals, whether anti-bonding molecular orbital is formed by the subtraction of overlap of atomic orbitals. Second, bonding MO has greater electron density in the region between the two nuclei of bonded atoms, whether anti-bonding MO has lesser electron density in the region between the two nuclei of the atoms. Bonding MO has the forces in this orbital tend to bring the two nuclei of the atom together. Therefore, the electrons in the bonding MO contributes to attraction between the two atoms, whether in antibonding MO, the forces in this orbital push the nuclei apart. Therefore, the electrons in antibonding MO contribute to repulsion between the atoms. It possesses Bonding MO possesses lower energy than the isolated atomic orbitals. Anti-bonding MO possesses higher energy than the isolated atomic orbitals. Difference between the terms bond energy and bond dissociation energy. The term bond dissociation energy refers to the energy required to break a particular kind of bond in a molecule, whether a molecule contains more than one bond of the same kind. Average value of the bond dissociation energy of a given bond is taken. The average bond dissociation energy required is the dissociative bonds in a substance is called bond energy. For example, in water there are OH bonds. Percentage ionic character. As already discussed, the most of the Most of the bonds have intermediate character between ionic and covalent bonds. The ionic bond has some covalent character and the covalent bond has some ionic character. The degree of ionic character depends upon the atoms forming the bond. When a covalent bond is formed between two similar atoms, the shared pair of electrons lie midway between the nuclei of both the atoms because both the atoms have the same tendency to attract the bonding pair of electrons. This tendency of an atom to attract the shared pair of electrons towards itself is known as electronegativity. In case the covalent bond is formed between two dissimilar atoms, one of which has larger value of electronegativity, the bonding pair of electrons is displaced towards the more electronegative atom due to unequal distribution of electron density. The more electronegative atom acquires a partial negative charge, whereas the less electronegative atom acquires a partial positive charge. Thus, the covalent bond develops a partial ionic character as a result of a difference of electronegativities between the two atoms comprising the bond. Such a bond is called polar covalent bond. Thank you.